actually a lot of other model problems, dealing with the droplets. So I picked these three, and because I thought that they may give you some idea, what kind of calculations you can do by using ANSYS. And the special thing in all these cases is that they include the uh, VOF method. So I actually, again want to, appreciate, the fact that, we are having some good discussion, and so it is a good feedback for me also, because when you point out something that, sometimes I'm also making a mistake, then it's useful for me. So last, before we broke up, we had some discussions, about some videos, and I think that these two people in the back, Anuj and the person name is Sai, they try to sort it out, by looking at the pictures, and so I am still not totally, convinced about how the video has been put together, but that's not a material, big materialistic, big important. But I think that this kind of a discussion I really appreciate. It means that you are paying attention and you are trying to, you know, see, what the actual situation is. But overall, I think that the message is clear, and that, what kind of flows that we can compute, and what is the basic equations and the numerics that is going into it. Okay. So I don't have any, you know, uh, solutions based on the LS method, but I think that is not important. Okay, all of them are based on the VOF, and so this is one more example, and I think, because some people want to look at it, can just go over quickly, and then pick up the next topic. So I think that by tomorrow, we should be able to finish everything, because we are going fast enough. And we are not really missing anything, but as I said, again repeatedly, that we should spend time if there is something that you catch, or you think something needs to be explained, or you think that there is need for discussion, because that's an important part of the whole thing, right? And this is not good for, all of you to, what are the other perspective, but also is good for me to, see what you guys are thinking, and if I am wrong on something, or I need to, understand. So this is again, is the third part, and that is we want to just simulate, the collision of two droplets. And again, we can always tie in that, where the importance is. So the droplets are, all over the place, and so in many cases, you have droplets and they're being created, and of course, when they come closer to each other, they are going to collide. And in this simulation, you will see that how you can simulate a slightly more complicated case when the two droplets are coming next to each other. So this is the kind of things that can happen when you have the two droplets. And you remember that a few days back, I think, you were asking about coalescence. So this is one case, in which you can see that the two droplets then coalesce, and they are shown in different colors. They could be the same color as well, but in order to show, how they can come closer, and then eventually they can form a single droplet. And then there is this bouncing. I don't see anything there in the picture. Then there's a reflexive separation, and there's a stretching separation. So the various kind of droplet collisions outcomes that are shown here. Uh, then we have to see that whether we are able to simulate these outcomes by using fluency. So now what we have is that this is a schematic So there is a radial axis and x-axis, and there are two droplets which are colliding with each other. And once this collision takes place, they can take a different shape, and as a result of that, the movement and the velocity that occurs, these are kind of you can say patterns of the streamlines that is a sketch. So we can look at then the kinetic energy and the surface energy is primarily a function of the surface tension, and there is a transformation of the kinetic energy due to the impact that occurs between the two droplets, and then that eventually converts into this merger that is shown there in the schematic into the surface energy, and the effect is the influential effect is that of surface tension. So this is again the setup that you need of this droplet setup, and you again have a computational domain, and we are considering asymmetry, axisymmetric droplets, but with symmetric rounding symmetry line, consider half the domain, and these are usual boundary conditions that we have in the computation domain. Most of them are pressure outlet boundary conditions. This is the uh, grid, very very fine grid, and so this is the close up of the grid just like in the previous simulation. Now again, as I said, that what are the important parameters that are important. Uh, so Weber number is always an important parameter in this case, and the other one is Reynolds number is always important, and then the other one is listed as a One storage number. And if you look at what we discussed in the second lecture, that this and this are somehow can be combined together, and also there may be some other combination, and this was given to you in the second lecture. So you can use these non-dimensional parameters to study the properties of this collision. Okay, so we are going to do I'm going to show you some results based on uh, the calculations that were made by my student, and these are the cases, and these are the conditions. So you can see that Reynolds number, One storage number, Weber number. This is very very small actually. The way it is, this expression is, this is the water, that is a liquid, and this is the properties, and this is surface tension coefficient between. So the droplets are that of water, and they're surrounded by air. So now you see here the case. So this case is that of coalescence, and then these other cases are that of reflective separation that I showed you in the first or second slide. So this is very rich in terms of the field is very rich, and actually there are lots of books and lot of papers, and lot of them are based on some older generation analytical solutions as well as some empirical relations. So again, you will find that the same theme is coming up in terms of the algorithm that we have used. And so in the previous two examples, same thing, the incompressible laminar volume volume of fluid method, and in every case we have used the continuous surface model for the surface tension, and third order upwind steam because it's a better resolution. First order implicit in the time integration, and the second order upwind in the solution of the energy equation, which is slightly different than third order upwind steam. This is third order upwind steam. And simple algorithm is used in all the cases because that is the one that we have. Now, there are variations of simple algorithm that are available in the Fluent that you know, but the formulation that I discussed in chapter 5, in the lecture 5, I think is the basic formulation that is being used in all these calculations. So, as I said, that if you want to try it, my impression is that they are really very straightforward. So, these three plus two more cases, five such cases were done by the student, with the other, and the other one was a little more complicated for the doctoral thesis. So you can see that how much, you know, computational work was, and there are some interesting ideas also came out in terms of basic research. But the complicated cases I'm not going to show you, which have to do with some aircraft applications, which I showed you that when the component of an aircraft hits the water or the ocean surface. So they were the final outcome after painting this practice. But these are actually very interesting results in terms of the fundamentals. So again, the procedure is the same. So once we have decided about the solver, we decided about various aspects of the solver, then we have to do the validation and also the grid independency. So you have to go through the same, you know, effects, the same kind of procedure. In every case. So you will see even in the other cases that I will show you on cavitation and so on, that this is just my philosophy always is that in CFD you have to first formulate the problem and then understand the physics that you want to capture, and then after that the what is the simplest model that you need to capture that physics and which code can have that model, and then the results can be trusted. So always follow these 4 or 5 steps, and I think you can use CFD very effectively. So again, you can see in these 3 examples that is what is being done. And so this particular case again, we have a coarse grade, medium grade, and fine grade, and then it shows that, for example, this one, the coarse grade solution is really bad as the flow evolves in time, and but coarse grade solution is really bad. So you need a medium or fine grade to really get the solution, and so you can see that the cell size is 50 based on the radius is 100 and is 150. So you have to have minimum cell size which is smaller than RB over 100. So this is a study you must do in order to make sure that you have the right amount of grade to have trust in the solution. Okay. The rest of the solver is very good. You don't have any problem with the issue of the terminus model. So this is the surface energy which is related to the surface tension effect, and this is the kinetic energy, this dimensionless time. So these simulations are conducted, as I said, based on the previous slide, or they are conducted on a medium grade because the medium grade is sufficient. And again, this slide shows that the coarse grade is really bad to do this calculation. Okay. So now accuracy of the numerical method. Now the next step, what is the next step after you have done this is the validation. The validation is a must, right? I don't use this one because but last year when I came, every time I used to give that analogy, validation, 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 like that film, entertainment, entertainment, entertainment. So if you remember that, I think you should always call it 3 times: validation, validation, validation is critical. So anyway, there is a paper here, and this paper has the solutions uh, that or that can be trusted for and it has a regimes of coalescence, separation in droplet collision, and actually uh, CK law has done enormous amount of work. I don't know whether anybody has heard of it. In droplet combustion, he is authority, and so this is a paper by him that we have used, published in Journal of Fluid Mechanics quite a while ago to validate. Reynolds number is 296, Weber number is 61. So now this is the experimental observation from the paper of C.K. Law that I showed you in the previous slide, and this is the droplets, and this is why huh? What? Who is not there? Is that right? It, oh, it should be there, but I don't know, it might got missed or something. Oh, I see. Yeah, I think the superimposition is there, so I think that might have messed up. Okay. Now those kind of things, these videos and all this thing, I don't do this. I have difficulty in typing on my cell phone. So anyway, so this slide is not there. You said, right? I don't know why not. But anyway, so this is the experiment by C.K. Law, and if you cannot see it, just let me know, then you can write it down. And so you can see that as the time passes, the, the droplets, coalesce, and after that they basically change the shape. And I showed in the schematic how these shapes are changed, and it is remarkable, if you look at this, that such a complex geometric shapes can be captured what are seen in the experiment. And so the tool is very powerful. And there is nothing, as I showed you in three different examples, there is nothing special was done except the implementation is done carefully. That's all. And all the capability that is there was used. That's all. So this can be done. And I think actually you can try and see whether you can reproduce it. So if you have a little bit facility, a little bit, way to deal with the fluent, and you have experience in doing that, these are very good examples of two-phase flow. To try, and they are complex enough. So once you do this, this is also a very good research problem, and also is publishable in a very good journal. Only thing is that you should be the first one to do it, right? Because if you don't do it, then somebody else does it, then it's difficult to publish. Then it becomes a repeat work. So which most of you know that even if it is a good work, if it is repeat work, then question is what is new. Yes. No, the way it is that if you want to calculate, there are various type of energies that are there, like in the previous slide, previous presentation. The kinetic energy, gravitational potential energy, and the surface energy. So if you take the momentum equation that I showed you in lecture 5, then there is analog of that in the energy equation. And if you use that, then separating these components is easier. But you don't have to do this. You can take the other other part and you can do this. Now, if it is and if there is no viscosity in the problem, then you don't have to use energy equation at all. The viscosity is involved. So that is the reason. If there is no viscosity, you don't have to use it. That is correct. Yeah, that is correct. Yeah, you see that it become like analog, that if you have momentum equation, and you don't have viscosity, then if you integrate the momentum equation, what do you get? What kind of energy? Bernoulli. So it is, you can similarly show that it is possible if you don't have the viscosity to integrate it. But you cannot use Bernoulli type of equation under any circumstance, because you cannot integrate in the presence of the viscous effect. Okay. So this is easier actually if you want to include and then, you know, separate various type of energies if you use the energy equation. There is an energy equation analog in the presence of surface. The first one I know, but second one I am not totally sure. First simulation that I showed you, in which, you know, there was explicitly written K, rho, K, S, and that is correct. I think it may be possible, because if you have all the data, say from process from the calculation, like the U, V, W, P, etc. Yeah, if everything is there, yeah, so it may be possible to do it. It may be possible. Yeah, I mean, you know, I don't know. I mean, it may be possible to do it. Yes, you cannot, of course, ensure the conservation of energy, as I said, if you have viscous effect. Then, you know, you have to allow for the dissipation. To be more accurate, you know, you have to allow for dissipation. So it may vary from problem to problem. In some problem, you know, it may be that the dissipation effects are very small and you can, you know, ignore it. Yeah, yeah, that is correct. Yeah, yeah, I mean, you know, it depends on the problem that you are looking at. And but if you include the energy equation, then you can use those quantities and you can get the information more easily. Actually. But the energy equation in this case is different than the energy equation that you are used to, because of the presence of the surface tension. Yeah, and I think that if you go into the fluent manual, then it might be, you know, I don't know which version of that it might be included. Okay, so the interesting thing here is that these results are as good as, you know, like the experiment, which is really surprising, you know, in the sense that, you know, that there is some great degree of modeling in it. So now you see that the radial deformation properties on colliding, and so this one you see that these are the, you know, pictures in time, and this is a video, and so you see that the colliding that is taking place of these two droplets in time, and how, you know, these surface changes in time, and you can capture all this very nicely with the volume of fluid method. So that is a very nice thing that comes out, and I think that there may be, you know, the mesh issues may be there. So as I mentioned to you, it's a medium sized mesh of R naught over 100, and so this evolution is going on, and this is all can be captured, and this is the video of this whole cycle of that is shown here from 0 to 4. Okay, all right. Now this is a further okay. So this is a further, same thing in time. This is the evolution of this. Now this is interesting here. Maybe uh, you guys can sort it out a little better. That you see that this thing here, uh, if you look at, it's going through, various aspects of it, and then you see there is a breakup that is taking place, and in none of these figures there is a breakup, but in this video there is a breakup. So it means that must be some instant of time in which this is occurring, which is not shown on these sketches. This one, which one is this? Yeah, H. What is this? What you are saying is that, yeah, what you are saying is that, yeah, what you are saying is that there may be again some kind of superimposition or something of the figures, because you are saying that if you look at that, there's a t equal to 6.43, and there's a, yeah, I understand what you're saying, that there could be a separation, and then there could be and yeah, and that is causing this kind of video. Okay, it's possible that that is causing it, but I really, you know cannot say for definite what is happening. But the interesting part of this video is, I think, that you see that, how this evolution is taking place, and now you look at the change in the, this is the original radius r0, which is a circle, and then how this is changing in time at the various Weber numbers. These are again at the various Weber numbers, the droplet shapes under the maximum deformation, and again they are very actually close to the one that was observed in the experiment of law. So the interesting thing is that the numerical method can capture these very complex shapes. So this is the Weber number, and then you have maximum radius, cross-sectional area of the ring, and thickness, etc. And you can compare, many of these quantities, you know, with respect to the experiment. So the calculation, all these Weber numbers, uh, they came out quite accurately. And then, as I said, this was done in a matter of couple of months. It didn't take that long. All these cases that I'm showing you, they were done in a very short time. So once this was done, this as a verification cases that you know how to run. So the actual problem, was very messy, which I'm not showing you here. But in case we have time, I will try to see if I can pull it out, from my archives or something. So that's where you have, complete splashing of these droplets because of the impact of some kind of a solid object, like a aeroplane and all that. And there you can, also show that you can get really some practical results. Yeah. No, I mean these that we have, we don't have, we are. You don't need a parallel computer. Actually, you can run if you have say 8 core i7, and that is good enough, and with a reasonable amount of memory. I don't know how many gigabytes or something of RAM. I don't know, maybe not more than a few days or something. Yeah, yeah, yeah. So it may take a few days or maybe a week or something. But they are uh, they are doable in reasonable time. Because most of them, in academia, it takes a few days extra. It doesn't matter actually, but it has to be done correctly. That's more important. But they were not used any HPC at all. As a matter of fact, you can do it on your laptop. It may take a little longer, and if you have enough memory on the laptop, uh, like nowadays, you can have a Dell or even a Lenovo or some other which are not that expensive, and I think they have enough 256 megabytes, or you can take a maybe with a little more memory, and then 4 core i7, that is sufficient to do the calculation maybe in a week or 2 weeks. You can see, estimated how much time is going to take. But I think the time that takes the calculation takes is not that critical, unless until you are working for some industry or some need is there. What is more critical is that it is set up right and you have the confidence in the calculation. That is the more important part. That is where the time is consumed. So you have to figure out where the data is, where the validation is, what kind of grid is right, and then what kind of things that you expect out of it. These videos are nice in terms of showing, and entertaining the audience. But the real thing is that whether your validation and the results that you get, and then what is the significance, physical significance of those results. So that is the real outcome that you're interested in. But these videos are nice because they also give you how the evolution is taking place in time, etc. And they are attractive in terms of looking at what's happening. But the major time goes into the really understanding the problem and formulation. But the main message that I'm trying to give to you is that these are the problems that you can do in your, when you go back, you can try to assign to a student, and should, they can do it, without, because the grid is straightforward. Most of the things are straightforward. And the other thing is that although they have the complex geometry of the of the uh, of the bubble and its deformation, they're all done on Cartesian grid. And so the VOF method that is available and the LS method that is available is for Cartesian. So you don't have to worry about that. That is also very straightforward. But if you have like complex objects, you know that how difficult the grid can be. So these are very really in terms of the whole mechanics of doing it. That's what my understanding is, that they have been quite straightforward. You know. Now I cannot say emphatically, because I did not do this calculation. But the student who did it is a smart guy, no doubt. But on the other hand, the impression I had in whenever we discuss this, that it was not something that uh, created any difficulty. Okay, so now you can see the other information, and for this one there is no experimental verification, but we have done enough experimental verification with the work of CK Law, so that was. So this is the variation with respect to this linear correlation. So what then he did it, and this was the outcome of his work, is that the change in the Weber number when this the non-linear part, how do you create a curve? So this is just basically fixing with a curve, which is basically a quadratic. So this may be of some value, if you want to use this curve later on, so that you can consider as the outcome of one of these. Now you can then develop, some kind of a system. So if you go into the Fluent, then you will also find that they have what they call is a spring dashboard system of modeling. Okay. So when do they use this spring dashboard system? Do you know? Anybody has used it in Fluent? They're already there. So spring dashboard system is used, for example, if you are trying to simulate, say, the, the coal and air. So what happens there is that the collisions becomes important. Okay. So they are not the droplet collision, they could be solid-solid collision. But in case of droplet collisions, what is the effect, how the collision deform, and how can you quantify that effect by some kind of a model system. So the spring dashboard system are very common, and they are built in almost every code. For solids, it's very commonly used. And also, in case of droplets, there are not many there. So the idea here was that since you are doing the droplet collision, can you get some idea of how to build a spring dashboard system for droplet collision? So that's where the research angle comes in, that all these modeling that you're doing and all these validation you're doing, can you get something new out of it? Okay. So what you see here is that you're deforming droplet, and can you build a spring mass system, and if you include the effect of damping, then they call it a spring dashpot system, and then equivalent that kind of system that can show the deformation by that spring mass and dashpot system to, so that in the future you can have that model available, and so in the collisions you can use that model and activate it when you're doing that problem. Okay. So that is the purpose of doing this. So the viscosity, if you are including, that is equivalent to the damping force, that is dashpot. Surface tension is equivalent to the restoring force, and the one that you have the liquid elements, that is the spring vibrator. So they have equivalence between this and this. Now electrical engineers, and the biomedical engineers do a lot. So they can take the entire cardiovascular system and build a completely electrical circuit to show the effect of, and that they have equivalency also. Okay. So like the blood flow may be, equivalent to, I am just guessing, a current or something, and the voltage could be, related again to some parameter. So and the resistance could be, the resistance of that is experienced by the whole cardiovascular system. So there are actually in the literature a lot of equivalences like that. So in this case, it is very common actually, and I know that for the solid-solid collisions, they are available in the fluent. Okay, so then this becomes a dynamic equation for a deforming droplet. So this is the inertia force, this is the viscosity, that is like a dashpot, and this is like the kx, which is the surface tension. So all the three physical effects become a part of this spring dashpot system. And then you can non-dimensionalize this equation, and then it turns out there's a very simple solution that is a harmonic solution, and then you can see that how good it is. by doing some calculations at different Weber numbers, and then some of these coefficients that I've shown you. I mean, in the system, and then you can see that how good the solution is with respect to for various Weber numbers in time, which is basically a solution of the harmonic uh, solution that I showed you in cosine and sine function, and with respect to time from the spring Dashpot mass system. And so you can see that the correlation is very good. Correlation is excellent. Huh? I mean, you can see that, yeah, I mean, you can read it, that what is the correlation. I have to use my glasses actually. I don't use the glasses. Yeah, so the fitting curve is the red one, and this is the calculation. Okay. So what the merit here is that as a result of these calculations that were done from the fluent, we were able to get this model, and then you can put that model as a UDF into the code, and that becomes a useful thing. So that is a very, very practical outcome that comes out of this research. So I think that that is very valuable. So see, many times what happens is that when we do some research or do some calculation, we have a lot of interesting results coming out. But then what is the end user, sometimes we are not clear about it. Of course, if the end user is some industrial product, it is okay. Like I give you an example, which we were involved in many years ago, and I think you will be excited about that. I don't have results here, but with me. But if you go on the website, okay, Google, and you type, you say Agarwal Okpara, it's a Nigerian name, Okpara, and then Bao, Bao, it is Chinese name, all right. So we are covering, 3 continents here. But anyway, there is a very simple formula there. Now, that is the reason I am giving you that example is because what useful information you can get out of all these simulations. Of course, they have a lot of merit in it. I mean, because whatever you get, and basically, you can train people, you can train your, students, and you can train, if the students are here, they can use it, for their doctoral thesis, whatever. But I'm giving you an example. So here the idea was to, if a surgeon, if you have a coronary disease and your artery is stenosis, the stenosis means, you have plaque. We are not going to go what the mechanism is, just simply from a fluid mechanics point of view. If you narrow it, then what happens is that the flow that is coming in, if it becomes a narrow tube, it becomes faster, right, because of the conservation of mass. So, and there is a pressure drop. So, if you put the catheter in, you can measure the pressure drop. Catheter is nothing but a pitot tube, right? So, you measure the pressure drop, and there is a formula that the surgeon uses when the patient is on the table, and that formula, it takes him a second, all right. So whether he gets this pressure drop from the ultrasound, which is non-invasive, or he gets the pressure drop from the angiography, which is the invasive, then they get this information, and that gives the information based on the pressure drop, and he knows the heart rate. It is a very simple formula, but basically the pressure drop is related to the size of the narrowing the artery. That's it, and it will not take a second. Even if you don't have a calculator, you can figure out how much is narrowing. And then he says, well, I know how much is narrowing. We need to cut it. We need to put a stent, or we need to go through a bypass or something. And this is a standard thing done. And this formula was put together on the basis of the Bernoulli equation in 1950s. All right. And again, you can put it in your Google and you put in Gorlin, Urlin, and they even have thousands of papers coming out of improvement. Now, a large amount of massive patient data is shown that if your blood flow is low, if you are a pregnant woman, or if you have some other conditions, it doesn't work. So now you go there and you use the formula, and this Gorlin equation, which is a simple delta P is equal A, the narrowing is equal to delta P, something, some constant. That's it. And this is true that 20% of the patients are recommended stent or surgery who do not need it. And in terms of real amount, it is, in Indian rupees, it will be in crores, a large amount of money and there is spent, but surgeon and the patient cannot take the risk. They said, go for it because I want to live more, right? Which is understandable. So, can the CFD do anything? Yes. So, what people have done is that they have written massive theses and massive number of papers showing all kind of streamlines, all kind of things, all kind of stuff. And what they have shown is that they have all this information, but what do you do with it? If you are sitting there in the operating room, what do you do with it? It doesn't work. So you have to do the old fashioned way. But if you take another approach, that you make these models in your environment, on your workstations, and do all these calculations, and then somehow fit all that data by a curve in the form of the same formula that was used, with some modification of the constant. And then you have a plot which shows that all the people who have a low flow rate or high flow rate, or you are in a excited state, because pregnancy or many other reasons, they all go follow the curve. And if you give that curve which requires as much time in calculation as the original curve, which means no time, then that is a real contribution of CFD. That's a real contribution of CFD. And that is what we did when we have that equation that is now after our name of 3 people. Those 2 other people are my students. So same thing I am trying to point out in this context, that this can be very useful, because what we are doing here is that we are coming up with this dashpot for a collision of a droplets which is already existing. This is not that we have discovered this methodology ourselves, but it was already done for solid particles and it is there in the fluent, but it was not done for the liquid. So now what you have done is they took that already existing knowledge, used the fluent, got the information and created a dashpot model for the liquid particle. So that is the reason I gave you this whole story to make some point here, that one can use this thing very creatively to basically use CFD for knowledge base that is useful. So this is the evolution of the droplet energy. I think that I didn't want to spend that much time, but again you can have all these calculations because you have all this information. These are for all various Weber numbers, the surface energy, the kinetic energy. Surface energy is due to surface tension, and then again you can have these correlations that are listed there in terms of the Weber number, which is almost a straight line. So you can go over, you have all these notes. So what is the message that we got out of this presentation? First of all, the same procedure. We had this droplet that we validated it, we made a grid independent study. We showed that we got all the same deformation as was in the experiment. And then we said, all this we got. What do we do with it? Right? Okay, of course, you can write a paper and that can help you in getting a job or a promotion, right? Or maybe you can help the students. But actually, in practice, is there anything that came out of it that is useful for the further work or further research? And what came out of is actually the Dashpot model. I call it Dashpot, but you can say spring mass or whatever you want. And so now that model is available. And again, we made an offer to Fluent to take it free, but I mean, they take their own time. They want to make sure that we are not talking bullshit. We are really done some work. Just like I was telling you, that our model is there now being used, the turbulence model, by a lot of people around the world, and it has gone into NASA codes. It has gone into the Boeing code of CFD, turbulence model, the Agarwal model, but Fluent has not accepted it yet. All right. So if Fluent accepted, then many of these people in this room will start using. All right. I have contacted them, but they have not accepted it yet. But I think it's a matter of time, because if the technology is good, they will accept it. But if the technology is not good, they will not accept it, and they should not. So the point I am saying is that there are various other ways of looking at what you do, so that you can contribute something by using CFD, not only for solving a typical problem, but also extending and generalizing it for the purposes that it can advance the knowledge or advance the base in some other way. Okay. So this last example that I put it in was that purpose, that I could show you that the entire deformation process you could do by a spring dash system. Okay. So we will close it here, and I think we are little bit behind, but not a whole lot behind. All right. So we'll try to again skip a lot of slides tomorrow on cavitation, but I think cavitation is of lot of interest to people. But the other one that is not of interest to anybody actually except one person, and that is the CO2 sequestration. So we will probably skip a lot of that and